So it will be the last presentation for today. This will be done by Alexey Brodkin, software engineer from Synopsys. Its presentation will be about OpenWRT. Let's say hello to Alexey. Yeah. Everyone tight.
Good afternoon, ladies and gentlemen. Today I will talk a little bit about OpenWRT, which was actually discussed a little bit on a different presentation today. And actually I think I thought that guy will be here today, but probably he forgot some other things with which he's busy. Okay, so my name is Alexey Brodkin. I work for Synopsys, and so let me start my presentation then. First, let's start from looking at what we are going to discuss today. And probably even before that, I'd like to make a couple of notes. First, I'm a systems engineer, so I know something about low-level stuff, like how hardware works, how low-level software works, but I barely have understanding of how works something like HTTPD or something. So probably that means you may know much more than me in this area, and you won't be satisfied with what you are going to see here because it might be a little bit low level for you. And another thing that I want to note, it will be pretty high level presentation because scope of things I'm going to discuss today is quite huge, and we won't be able to deep in low level details of everything, even though something I would like to highlight. And again, probably it will be of interest at least for some of you. So what we are going to talk about today, a brief introduction of myself, then we will figure out why I'm going to talk about OpenWRT, actually why I was involved in the first place, then what is OpenWRT at all, historical overview, because I think it might be important and interesting as well. And then we will come to the most interesting parts about how actually embedded system and in a bigger picture, how any device which runs Linux starts from the very beginning, from power on to the state when it may execute something big and fancy like, again, HTTPD or something else. From that, we will understand actually which components we need to build to get everything up and running. That will bring us to the discussion of the build system of that open source distribution. And so then we will cover a little bit how actually it gets deployed on your target device, because it might be interesting as well. And finally, we will make some summary, what is good there, what is not that good, and a couple of tips and notes so that I think could be useful and interesting. So talking about myself, I work at Synopsys in St. Petersburg, in a group which is involved in open source development for our CPU cores. I've been in embedded developments for about 10 years, probably a little bit more. And so what I do currently in Synopsys, I support Synopsys development boards in Linux kernel. These are drivers, platform stuff. I was the person who made a port of U-boot bootloader for architecture. Then I contribute a lot in Buildroot build system, and since uclibc library is the only C library that we use, so I have to deal with that from time to time, deal in terms of as a developer, but not as a user. I use it essentially daily. And so finally, OpenWRT, that's the thing we are going to talk today. That was like a summary of all the previous components. So previous components were important for me to know and to have experience with. It helped me a lot with OpenWRT. So what is that thing, and so why actually I started to think about that, and why I was involved in development. So in Synopsys we have ARC CPU core, which might be configured in such a way that it may run Linux kernel. And so also we know that some of our customers who use our IP core in their SoCs, they build those SoCs for network-oriented devices like wireless routers and some network switches and smart switches and so on. And recently we started to get more and more requests about, okay, so guys, do you have OpenWRT support for your architecture? Because we want to use it in our product. So the decision was made, if we don't have it, let's do that. And what is that thing? Again, I think Pavel mentioned today pretty obvious thing. If something is mentioned on Wikipedia, so why don't we just use that definition? So OpenWRT is embedded operating system based on Linux kernel, primarily used in embedded devices to route network traffic. The main components are Linux kernel, uclipsr, Musl, and BusyBox. So that's a very essential part and brief description, which is a very good one. And just for you to get some impression, what is interesting here, this embedded Linux distribution supports more than 10 different CPU architectures, more than 40 different platforms or SoCs, and more than 1,000 devices. And so compared to other distributions like desktop ones, so like Debian, Fedora, and so on, when I talk support here, I mean binary packages for all these 1,000 devices actually get built automatically with build system. It is not that you may, with some hacking, make it work on your special hardware. No, here we make everything built, and you may just grab that image and use it, deploy on your device, and use it. So probably that's the most, that distribution which builds for more platforms than anything else. Another nice thing, it may run on very low power and restricted devices, restricted in terms of hardware possibilities, like we need a very small amount of memory, both for like RAM and flash, and we don't need a lot of megahertz compared to desktop distributions. So another nice thing, it is package-based, so it is exactly the same thing as you have in this desktop distribution. When you just, if you want to install a new package, you just say, please install something, and you get it. You don't need to compile it yourself. You use usually a repository of these packages in the internet, so you don't need to install anything manually. You just issue one command, that's it. Now looking back at history, so what we may see here, project started more than 10 years ago, and it started in Germany when the first wireless router made by Linksys was implemented such that it used Linux kernel inside as a base of its firmware. And since Linux is GPL based, community started to push Linksys to provide sources so they may reproduce the same image. And so finally, after some discussion, sources were disclosed, and people started to hack on that, making it better, adding new packages. And how they did that, they just took existing back in the day Buildroot build system and started to add support of more hardware, more different packages. And they continue to leave that for a couple of years. And something that started as a hobby of a couple of German guys finally became to the state when big companies, most probably it was Atheris as a manufacturer of SoCs and Netgear as manufacturer of consumer devices, they started to use OpenWRT as a base of their firmware, and so they continue to do so. And with years, more and more companies joined them. So today, I think about 50% of consumer and prosumer wireless devices, wireless routers, they actually use OpenWRT in some form, probably some older versions as a base of their distribution. And what is also important, big vendors use OpenWRT for building their SDK, which they provide. For example, SoC vendors provide to companies who produce actual consumer devices. So we see a lot of companies join them, and probably everybody will use that finally. So then, since that project was driven by real democratic things, so every developer was equal, at some point they were not able to agree on anything, and we saw a fork that may, but hopefully two projects will be merged back. Still now, those who follow that topic know that's how painful it is, because you don't need where to send patches to one project or to another or both, but code base is still a little bit different. That was, I hope, not that long introduction, and probably this is one of the most interesting parts of my presentation. Here we will talk about boot process of a real hardware device. On that slide, you may see different stages. So this is not as simple as you press a button, you power on your device, and then you see a prompt in console or nice fancy window asking for your login and password. No. It happens in different stages. And we'll go through all of them, and we'll figure out why we need that complicated setup, but not something straightforward which could be completed in 2 stages. So first, essentially, we power on, and what happens then, CPU jumps to some location in memory, which is configured as a reset vector, and either starts to execute code there or jumps to the place where first part of the code exists. Then that thing passes control to boot ROM, then so-called SPL or secondary program loader. Then we go to full-scale bootloader, then finally Linux kernel, which finally starts user space. And let's try to find out why we need that complicated system. The thing is, when CPU starts, pretty much everything is dead around. The only thing that works is CPU core. Okay, what's that? That is nice. Okay. So first, when we are here, the only thing that works is CPU core. We don't have access to anything. In the best situation, we have some on-chip memory, which we may use. But still, first code which gets executed, this is a part of the ASIC, part of the chip. And actually, that's a ROM, which you cannot modify. And because of that, we have to build it into the FPGA when we produce it. So we tape out with that code, which means we have to be completely sure, not pretty sure, but completely sure that it is flawless. Because otherwise, if there is a significant problem there in that very little piece of code, we go to another tape out, which costs us a lot of money, and we spend a lot of time on that. That's why, and it's also to keep the silicon area smaller, we keep it small and simple. And because it is small and simple, it cannot do a lot of things. It may do something very simple. So what this thing typically does, it reads something more capable, larger from some usually storage which you may modify finally. So this is not that important to have it completely bug-free, because in the worst case you may update that with newer firmware. Again, since we are very limited on resources, we may access something simple. So typically, we are talking here about the first page of the NAND flash, or preferably NOR flash, or it might be like the very beginning, the very first block of SD card. We may afford in our firmware. And finally, and we don't do any initialization usually here, and to load something from external storage to some memory which we may use for execution, we need either to have on-chip memory, but not every CPU or ASIC may have it. So what happens, for example, on x86 CPUs, what they do, they just lock cache lines and use it as a on-chip memory. And so then we execute code right from flash, even though it's right from cache, even though we didn't load it from RAM, which that cache backs up, but we load from some separate external storage to cache, then execute it, then we finally enable cache when we have DDR ready. And so we may finally use DDR for something fancier. And at this point, we get a secondary program loader loaded, and we may start its execution. That thing is more capable and can do more things. It may have, for example, more complicated driver which supports basic file system like FAT file system, or full-scale driver for NAND controller. And that means we may load more data, and by that time we may also initialize caches, DDRs, clocks, so we may put downloaded data in DDR from which we will execute it later on. And so that is a significant difference to the first ROM. Boot ROM. And you see we may get data from flash SD, probably USB, but not very likely, because USB stack might be more complicated. Probably network again, probably not. And on some systems, actually, SPL will be used to load Linux kernel, because basically that's enough. why we usually don't do that, because still we have some limitations, because we have to use smaller image, which we cannot load with boot ROM. I mean, bigger we cannot load. But SPL may load full-scale bootloader. Typically on x86 it will be grub, on most of the other systems it will be U-boot. This is very powerful thing. This is a sort of operational system or something like that, because it has tons of different drivers built in. It has scripting language. It may support different fancy things, may already set up and prepare more memories, may even initialize a video controller and pass just pointers to that frame buffer to the Linux kernel. And all these possibilities allows us, for example, to implement fail-safe scenarios. So first, for example, we try to download image from SD card. If we cannot do that, or checksum doesn't match what we expect, we go to network. If we cannot go get it from network, we go to flash and so on. Before that, we were not able to do that because we didn't have drivers, we didn't have access to enough memory to do that. And so that thing, what it does, it prepares everything to start up Linux kernel, and if not SPL, then this full-scale bootloader loads Linux kernel. And finally, Linux kernel starts, and this is significantly bigger substance. We are talking about megabytes here compared to kilobytes before. That thing could be modified essentially because we want to use newer kernels with newer firmwares. Full-scale bootloader may download from anywhere, and what Linux does, it starts and continues its bootstrap process. Again, it does a lot of initialization, first of the core, then of platform devices, then different drivers, and finally we are ready to run the first user space process, which is basically init. And when we are ready, we start init, and we are finally in user space. And then what happens here compared to, let's call it normal desktop distributions here, because we have to run on such a wide variety of different boards. With first thing we do, we need to figure out what is our hardware below us, because depending on that, we will need to do different things. Again, we are targeting some particular devices, and we don't do generic initialization and probe 10,000 different drivers. We just want to do very straightforward initialization of devices that we do want to initialize, nothing more. So how we do that? Normal procedure is to have a device tree blob which specifies our current platform, our current board. So what we do, we just parse it, and from model property we read some string, compare it to something that we expect to get, and depending on that we proceed with initialization of this and that. If that is not possible on some systems, we may use output of CPU info, because it may contain some hints for us to decide what is our hardware. If it's not the case, or this is not enough, for example, on the devices which may survive through, say, more than 10 different iterations, each differs with very minor modification, like different memory IC or different network switch or something like that. What we do, and that is possible because probably the same way, not probably, but definitely that's way manufacturer acts. They write some magic value or string in some location into the flash, and we read it, compare it again with some known values, and that way we decide which version of hardware we run it on and what we need to do. Once we know where we are, we continue initialization. If that's the first boot we do, we run one set of scripts, otherwise we run something else. First time we do something different because we want to prepare board for the user which will be usable. For example, we want network interfaces be up and running, otherwise user will need to access these boards via, for example, serial ports, which is usually not exposed at all. So that's why we need at least to have network interfaces, wired interfaces working. And even though I point here that we enable, we not enable, but detect wireless radio, we keep it turned off for quite some time before user explicitly turn it on. This is sort of a security concern, because otherwise wireless network will be open and everybody will enter that device and will do whatever he wants, which is not the thing that we want. First, we want to be that wireless network set up properly with passwords, and then we allow others to log in. Then we automatically load different modules that we need to work with peripherals, basically different drivers which were not built into the Linux kernel image. And then finally, these things that I was talking about, like DHCP server, HTTP server, SSH, whatever you want, print servers, whatever. And so also in that distribution, compared to some closed source solution, you have user prompt. You may use it through serial ports, SSH, telnets, and you may do whatever you want. When we went through that boot procedure, we mentioned a couple of companies that we need to build. So boot ROM, essentially, we are not building because it is already in a ROM. We can't modify it. We don't care about that. We have what we have. Then we need a secondary program loader, full-scale bootloader, Linux kernel, file system, additional packages if we want them, and finally images which we deploy on the target. I don't mention here separately different bootloaders because, for example, in case of U-boots, sometimes or even usually we have them combined because basically this is a combined image. First part, this is SPL, and then normal full-scale bootloader. And this is very convenient because SPL knows where to find more powerful bootloader. It is just with a offset of something. But what is important? We are going to build stuff for another platform. And we will be building most probably on x86, or definitely it will be x86 CPU, but it might be something with Linux on top of that, Mac OS, or even Windows. And that basically means, and we will build for MIPS, ARM, ARC, SH, I don't know, you name it. Which means we will do cross-compilation, because otherwise, how we are going to build that? Which in its turn means we need to build cross-tool chain, which in its turn requires some helpers. And why we need helpers? We may actually rely on the stuff which is installed on the user machine, but then a lot of assumptions like, okay, we need tons of different packages and preferably of specific versions. Otherwise, we may get problems during that long build process. So that's why we prefer to use something bare minimal like Make and GCC, and everything else we build ourselves. So we build for the host without cross-compilation, then we continue with that build tools, building of cross-compilation tools, and then we finally ready to build images. And so probably then we will build SDK as well, but basically this is a tool chain processed specially, so it is relocatable then, and it will allow our users to build additional modules or our user space software without requirement to build that huge thing. And so now speaking about OpenWRT build system, as mentioned in the very beginning, guys decided to use Buildroot, and Buildroot's very nice and clean project, at least as of today. And I enjoy using that tool a lot. But what happened with OpenWRT? First, they started to use Buildroot more than 10 years ago, and as I understood, even Buildroot back in the day was not that nice as it today. And another thing, very limited amount of developers started to work on this OpenWRT, which meant they did a lot of work, and they didn't actually think back in the day about problems that they may face later on. And so they basically implemented a lot of ad hoc solutions, which later on became constructions of that thing. Even though this is a Makefile-based build system, in Makefile's developer, but not user, essentially will face these things, or even these kind of things. Even if you have quite a lot of experience with Makefiles, you will have a very hard time trying to figure out what's happening there. And what is also important, if that piece of code, if we may call that way, will be executed at all, because it depends on actually if that target was ever called, and then if that dependence was there, so it's hard to analyze what happens. And another interesting thing of that build system is usually in Kconfig builds, Kconfig configured build systems like Linux kernel, libc, and like BusyBox probably, but I'm not sure about BusyBox. we have so-called dev configs. So these are minimalistic configurations which are targeted to specific boards, specific configurations, and this is useful because you don't need to do configuration for each and every case yourself with your hands. But here we don't do that. As I was told by one of the developers, the reason for not having explicit dev configs because they use implicit dev configs. What that means, when you select some platform, this platform already defines some features that it requires. And then together with default options for all the different modules and parts of this distribution, you are getting something by default. You are free to modify it to your preference later, but that's what you have, default configuration. And again, the reason for that was we don't want to maintain more than 1,000 dev configs, because then it's a nightmare if you want to change at least one option. And for limited amount of people, that's a huge amount of work that these guys don't want to do, and probably that's fine. So it basically, I think, has nothing to do with that hell, but this is another consequence of a lot of work being done by a limited amount of developers. And so then what happens when you're ready to build something? So first you run make menu config as you do it with Linux kernel. Then you select your configuration, and for users this is super nice and convenient. You have you use your arrow keys, select what you want with space, then save it, and then say make downloads. You download sources for different packages, and then you fire make, and everything automatically gets built. If you don't have any errors or missing dependencies, which sometimes happens anyways, you may build it. And again, what I mentioned, what is interesting today, you may actually run this thing not only on Linux host. It works perfectly well on macOS, and some developers of OpenWRT use macOS as their main system without even virtual machine. And what is even more interesting, with Windows 10, you may use so-called Windows subsystem for Linux, or vice versa, I don't remember what's the proper name, and build that thing there as well without virtual machine, which is, I'd say, pretty nice. So you don't need to install virtual machine first. So it makes it even more affordable and easier to people who want to start playing with that. So once you go through all that, build steps like sources get extracted, patched, configured, built, and then we install it. What's important to mention here as well, as all build systems, we install not only things to the target folder, which will be used to create a target file system, but we also install something. Host tool essentially go to a separate location, and also we have a staging location where we put, for example, libraries, shared libraries, which we will use later on for linking different applications. And the same libraries later will be used on your device in root file system, and so that's how it works. And so then finally, you're ready to create a package which you will deploy on your target. Depend on your device. For example, typical router will be use NAND flash, where you just put built image, binary image on with some offset in that flash. Some devices, especially development boards like Raspberry Pi or Aura boards, we use SD card as a storage, because this is much simpler. You don't need to flash something in runtime. You just stick SD card in your laptop, copy binary image with DD command in Linux or special utility and Windows, and you are golden. You stick it into the your development board's power on, and it runs. That is as simple. In some cases, it might be more complicated, but usually it is not. And so what is also, by the way, nice, if we are talking about real consumer wireless routers, that build system prepares files which you may use as vendor's normal update file. So you don't need to hack anything. You just provide that binary as following instruction provided by vendor, press update button, and in like 1 minute you have that OpenWRT stuff deployed on your hardware. So it acts like a magic. And here talking about development, talking about build procedure, there is one special place, which is Linux kernel. I think this is also interesting part of that presentation, because again, we are building for more than 1,000 devices, and that is not simple. Usually when we are talking about building kernel, what we do, we say make something dev config, and then we build. But here again, we don't want to do it because of at least two different reasons. The first reasons, not every board is supported in upstream. That's not good, but that's what we have, and we have to deal with that. The second reason, actually, to build Linux kernel for 1,000 boards, that is a very time-consuming exercise. Even if you have very powerful machine, it will take, if we assume that every kernel gets built in 1 minute, I think it will be like 3 days to build for everything, which is nice for cut and release. But if we want to have nightly testing and actually guys have infrastructure that built it every day, then it means we won't be able to do that, or we'll need a huge farm. And for open source projects, it is not something that they may afford. So what we do actually, we build only for platforms. And so that's how we are getting from 1,000 builds to 40. And so that's what we do actually. But then when we have image built for platform, but not for the boards, we have somehow to differentiate it for different boards, how it run on that wide variety of different devices. As I mentioned, either bootloader or early on kernel execution, we will parse device tree blob. So what we may do, we may either provide proper device tree blob with bootloader, for example, with U-boot, and that's again preferred way because this allows us for more flexibility and visibility of how it happens. There is no magic behind that. Otherwise, if we don't have U-boot bootloader, or for some or another reason we don't want to do that, we may actually build separately Linux kernel, separately a lot of device tree blobs, and then we just patch in binary in Linux kernel. And so with a very simple patch in Linux kernel, that is possible. And then we build kernel one time, and then for 20 different boards, we just patch in different small binaries. It takes like 1 second, and we are done. Or in the worst case, what happens, we are trying using some logic and some signs of difference hardware, try to determine where we are running on runtime, as I explained it before. And we use one image for different boards, still trying to figure out where we are. And another problem with Linux kernel, which I already actually mentioned, we don't have everything upstream. It is not only about dev configs, but also some functionality which is missing for different boards or some generic stuff. For example, as it was mentioned already, that problem with airtime. So what's the name of that? So fair usage of airtime for different clients. It is not in upstream yet, but we may just add patches here of the tree, and so by the time it gets upstreamed, we just remove these patches. And so we do. So we add quite some patches for everything because something is not dependent on platform. For example, like these patches. Or we may have something specific for platform that might be something missing from upstream, or that might be even board-related stuff. Specifically, and usually these are configuration options, like we want to enable something, but still most of the stuff will be here in these configs. You see configs base of different versions. So this is for kernel version 4.4, 4.1, and 3.18. And folders with patches here as well. So what we do, we combine all together this configuration with probably part of configuration here, and so this configuration in one .configuration file and use it for kernel configuration. The same we do with patches. We apply first patches from here, then from here, and so finally from patches here if we have them. That's how we build Linux kernel. Now talking about those of the three patches, there is a quite clear understanding about that is not really good and nice, but still we have quite a lot of patches not upstreamed yet. But if we look closely at these patches, we'll see that actually a lot of these patches backported from upstream, because the point is we don't want to switch kernel every 2 months when Linux cuts new releases. And so we prefer to use stable kernel. So as of today, this is 4.4, and for this 4.4, we want to apply a number of patches. Some of them security fixes, some of them functional fixes introduced in later versions. And so what we also see 11 patches awaiting upstream, because we want sometimes patches to be here earlier compared to when it gets to the stable branch. And so inevitably we see a lot of, not a lot actually, a couple of patches for different architectures, and we see these 15 patches, that's not that many, and for storage subsystem and drivers, and also some for networking. Again, there is no real reason to keep these patches off the tree except the fact that somebody has to upstream them, and it requires some work. Sometimes it requires significant rework. So we have some our issues fixed, and we are pretty happy waiting for a day when somebody does this work. Hopefully someday it will happen. And so actually I'm pretty close to the end, and that's a sort of a conclusion of this introductory discussion. What is good about this distribution and what I like, it is vendor-independent Linux distribution. There is no big company behind that. Indeed, we see a lot of vendors use that, but these are not vendors who define where we move here. This is a group of people and community who decides which way to go. And if you have enough contributions and people know you, you may provide more ideas. Even they don't know you, you may propose something, but not sure if it will be taken with enough attention. Another very nice thing, and so what makes OpenWRT very affordable, we don't need a lot of resources. Before the latest release, we have built images even for devices which sports like 16 megs of flash and RAM, and I know devices which run about 200 megahertz. That's not that many. Even though in the most recent release support was dropped, but I know for sure that support of these devices will return back, because why not? We may just not build that many packages. What is also interesting, a lot of different devices support it, and what is even more interesting, some devices you may really find in nearby computer shop or mall. It may cost, and it actually costs less than $20. So pretty much everyone may get a device which already support it. And so as for end user, it is very nice, because if you want more features, you install new packages. And so what also now is you have very nice Lua-based web UI, which allows you to set up those additional functions that you install. For example, you install print-server, you just install a GUI part for that, and you are done. You just select your printer model and it works. You don't need to hack CAPS configuration files. It is super convenient. And two other items. This is just a continuation of the fact that it is a Linux distribution without limitations. You may use normal Linux tools. And so what I'm talking about here, if you have something like Cisco thing, you're pretty much limited with the functionality that's allowed to you. So you may use special commands to do something, but you are not allowed to use complicated and ugly shell script. Here you may do that. You don't want shell script, okay, you install Python and use Python script. It is possible, why not? And another thing which is also important, and I think very important, and already was mentioned on different presentations here, guys from this team, they contribute a lot in Linux kernel, and they are really forefront of wireless networking development in Linux kernel. So because of them, because of their customers, we have pretty nice networking stack, and we see it developing more and more with time. But there are downsides as well. Small amount of people work on that a lot, and that's why they don't care much about stuff they know quite well. It is a pain for a newcomer, but that's a problem. That's a problem for a newcomer, but people who implemented most of the stuff, they don't care. They may remember what they did and why. So that's here, and that's another thing. So people may contribute something and submit patches, not even submit, but accept patches like remove this, add this, or even without that explanation, just remove. And outsider developer will have a hard time trying to figure out why that, what idea was behind that, and this is not really nice. And I know a couple of places which even core developers, they don't remember why this feature is there. So something could be dropped because, okay, nobody cares, nobody knows what's that, and you don't have enough information in Git to figure out if it was really needed for something or not. And another big problem for both vendors and end users, there is no clear release cycle. So as big distributions, they release like twice a year. Here we don't know when it happens. It may happen, may not. So you cannot predict when you get something new and stable, because release means we have a couple of RCs, we have some stabilization periods, and that's don't know when it happens. And most of people, they don't like to live on the edge, like on the master branch. And so I will actually propose you and will encourage you to become a part of that and try that at least, because this is very affordable. You just get cheap equipment. If you prefer, before that, check that this hardware is supported, you just grab it, install build image, and you enjoy it or you don't enjoy it, and you improve that then. Or otherwise, what you may do, you may get something which is not well supported or not supported at all and start hacking on that. Community is very welcome and just send patches. That's all simple. Development on GitHub and on Lede is on a different place, so still this is very simple. And this is mostly for readers of this presentation who will read this offline. A couple of interesting links which might be interesting because contents could be a little bit specific. For example, I was pointed to that discussion, which was a real precursor of OpenWRT creation. A couple of complaints for core developers about these links is sources of new router. I think that's pretty much it for today for my presentation. If you guys have any questions, I hope somebody will ask.
Thank you very much for these detailed presentations, and now it's time for questions.
Thank you once again. My question is related to OpenWRT update system. How does it handle configuration files and other stuff that could be changed by the user? I have studied it once, and if I'm not mistaken, it uses overlay FS to store user modifications on top of those default values. Could you please explain the design considerations behind that?
Well, to be honest, that's not the kind of details I know very well, because I made a port of for another architecture, and for us yet we don't have those complicated updates things, but what I saw that they use scripts that do some patching and modification. As for overlay FS, I think it is mentioned somewhere here. So what they do have, they have that ability to roll out changes that you made, but frankly I don't have enough knowledge about that. So again, I'm more on this system stuff.
Okay.
Sorry for that.
Next question.
Question about mostly security. How your system handles new security patches?
Yeah, that's
in Linux 3 and from up to bottom, and how the certain devices with your system can be patched with the security updates.
Okay, so first part, how we apply patches. That simple infrastructure is in place. You just drop another patch in the folder, and next time you rebuild kernel, this patch gets applied. So that's how you build it. And so then keeping in mind that this is a package-based distribution, you may update even core packages. So what happens, you build your newer kernel, it gets packed into a package, and you install it on flash. Then you press reboot button or reset button, or you invoke this reset like in GUI. Then this board gets reboot, new image loaded from flash, and you are with a newer kernel with that security patch in place. That is very simple.
Okay, thank you. The next question.
Thank you for the presentation. First of all, I have experience with OpenWRT, both personally and professionally, and as a router distribution, it's absolutely fabulous. Thank you. But it's kind of maybe a request. Your build system is so much better than Buildroot's.
Better or worse?
much better, much better. Yeah, seriously. In comparison, it's Builder is painless. OpenWRT, when you develop product for it, it's easy. But here's the thing: in a commercial development, I cannot use it in anything but a router, some box or whatever. Could you guys please split your very, very application-specific userland from your awesome build system, please?
Well, again, I'm not the core developer, even though I contribute from time to time. Well, you are welcome with your patches. You propose a way to split this, and you get that. Essentially, again, as it is defined in the Wikipedia article, this is mostly targeted on wireless devices.
I did ship devices with OpenWRT. I know it's beautiful, but very, but potentially your build system is awesome.
But you know what? Actually, I discussed that problem, or not problem, but what exists in their build system with the real core developers of OpenWRT. And what they told me, when I pointed them to Buildroot today, they told me, well, if we were about to start something new from scratch, we would use Buildroot as a base, because this is very clean, structured, nice, and pretty well documented project.
Yeah, exactly. But featureless, I would say, in comparison to OpenWRT.
There is another target for Buildroot, right?
Excellent. Thank you. The next question.
Thank you for the talk. I have one remark and question with logically links to it. Johannes Berg, it's maintainer of wireless subsystem, on Linux Plumbers conference announced wireless backports project. I don't know, maybe it was already set at that time, but he asked people to get involved in that and backport wireless drivers to older kernel. And the question and continuation question of this, so I noticed many presentation has relied on 4.4 kernels, but none of them explains why. Because there is a nice abbreviation, LTS. So it means long-term
I meant
support.
to tell about that, right? So and if you remember one of these slides, it was in the very beginning. So if you take a look at Linux versions here, you will notice that this was stable, this was stable, this was stable, and this was stable, and the next one will be stable, LTS, I mean. And the only thing which was not LTS, it was that one, but there were reasons for that decision.
Yeah, but I mean, stable and LTS kind of a bit different things, because we have 4.8 stable.
Okay. What I told was not correct, LTS essentially.
And actual question is, you have 63 patches backported from upstream on one slide. Why so? Why not to push them to LTS kernel actually for everyone?
Well, first, you know how things, let's call it newer things, but actually small patches get into LTS branches or any other stable branches. They go there through Linux master tree. So essentially, once this patch gets upstream for a newer kernel, it gets backported. And again, you actually mentioned very interesting thing and important, I think. In OpenWRT, we use wireless drivers from wireless backports, which means even though we are on 4.4 LTS, wireless drivers are from the, not Linux Next, but from very, very recent kernel release. So with all the features and improvements and fixes for wireless drivers, that's another important point, I think. Thank you.
Okay, thank you. Another question? Еще вопросы? Okay, so please push the last mic for these presentations in this report evaluation, and pull out this this list and provide to the girls from the reception.